Okay, so where did we leave off last time? Where did we leave off? The Pythagorean theorem, right? I-47. I-47. I already gave you the proof last time. Let's just go over the proof again because we did it a little bit quickly. But let's just do it in GeoGebra once and for all, and then you'll see everything that's going on. Okay? So I'm not going to write anything. We're just going to compute in GeoGebra and see what the argument is. Okay, so first of all, we'll get some points. Here's a point A. Here's a point B. Here's a line segment between them. You can see that okay? Let's drop a perpendicular at A. So we'll make A the right angle. And then I'll choose an arbitrary point right about there, C. Okay, and I'll connect B and C. So A is our right angle. We have this triangle ABC. And the question is, why is it true that the square on AB plus the square on AC, in other words, plus in area, equals the square on BC? Well, step one, let's draw those squares. Whoops. Let's draw those squares. Where's my drawer tool? Oh, here. Polygon, regular polygon. I want a regular polygon on this segment. No. I want a regular polygon from A to B, or maybe from B to A. What happened? Regular polygon from A to B with 4 sides. Yes. Why can we draw a square? Which one? The one right before. The very next thing after drawing squares is proving the Pythagorean theorem. Okay. So I-46 says we can have access to this tool, at least for squares, this regular polygon tool that'll draw us 3 squares. And if I get it in just the right order, beautiful. Okay, this is why it's called the windmill proof. So we've drawn the 3 squares. What's the next step? Who remembers the next step? Anybody? What's the key idea? Yeah, go ahead, Jemima. Yes, through A. Let's draw, whoops. Let's draw a perpendicular from the top point to the bottom of that, either here or here. What's the purpose of that perpendicular? Say it again. To make it actually chops this big square into 2 rectangles. The way I've drawn it here, there's a thin rectangle. I mean, all of this is up to like it doesn't matter what the actual this is all this is a universal proof, right? It's not this particular proof that matters. But what we've drawn is in fact a little rectangle here, BKJH, which may not be the letters I used last time. And what's interesting about BKJH? Exactly. This rectangle, let's compute that area. Let's compute the area of B to K to J to H and back to B. Please. Please compute the area from B to K. Can I just not see it because the square is there? Okay, let's see. Can I not show the square? And now let's try to compute the area from B to K, please. Oh, I have to construct the polygon first, and then I can compute its area. Fine. B to K to J to H, back to B. That's one rectangle. And what's the area of this rectangle? It's some number, 9 point whatever. And what's the area of this square? Same value. Okay, that's what we have to prove. Okay, so we're going to prove that these 2 areas are indeed the same. And the question is, how? Go ahead. Yes. This square is going to be equal to this rectangle. So let's draw that in. This other rectangle, there's a symmetric argument that says that this other rectangle, so those 2 rectangles make up the full square. And this rectangle, whatever its area is, 33.12, what do you think the area of this is going to be? Okay, so that's why this proof works. The two rectangles sum to the big square. These two rectangles sum to the big square, and each of the rectangles realizes the area of the square on the other side. That's what we're trying to prove. Exactly. That this square plus that square in area adds to the big square in area. And we're going to literally chop the big square into two rectangles, which have the corresponding areas. Okay, so the last thing to do is to prove that BKJH indeed has the same area as ABED. And what does Euclid do for this? Anybody remember? You can look back at your notes from last time. Jemima?
Lines between C.
Yes.
CE and BF.
Yes. Let me not draw BF just yet. I'm going to draw this triangle from C to E to B. This is the key idea. If I drop this diagonal over here, that makes a triangle from E to B to C, and then back to E. Everybody see that? What is the area of that triangle? The area of the square is about 10. That triangle lives on the same parallel line as this parallelogram and has the same base. Everybody see that? And there's a theorem, I-41 or something, that says that the area of a triangle on the same base as a parallelogram and between the same two parallels will be half the area. Okay, so when I ask for the area of this triangle, what do you think I'm going to get? A little less than 5, 4.93. You double 4.93, you get 9.86. Okay, what's interesting about this triangle is that there's another triangle that's just like EBC. Jemima was telling us where it is. Yeah, the H to A. Yeah, it's not the same labeling as what we had in class. H to A. Okay, so let's draw in that triangle. So I'm going from A to H to B and back to A. And that's another triangle. Now it's starting to get a little cluttered. Let's see, can I zoom in just on this part? So this area is the area of this triangle. This area is the area of this rectangle. I'm going to try to move things around a little bit. Okay, and this new triangle ABH, what is its area? From A to B to H, what is its area? 4.93. Why? Because it's the same. Did you say it's the same triangle? Yes, it is the same triangle. It's the same triangle. Why is it the same triangle? Why are these two triangles congruent? Side, angle, side. Why side, angle, side? Look at one of the sides, the thin side. Why is C1 the same as H2? If that's what they're called. I don't know what they're really called. Because they're on the square. Why is, so we'll look at BC versus BH. Right. And now what about the angle? Here I have an angle. Let's see, can I draw in an angle from E to B to, no, that's the wrong way. From C to B to E. Oh, please. Pretty please. From C. Sometimes it helps if you ask politely. So that's one angle. And that's 151 degrees in this picture. And the other angle is from H to B to C. To A rather. And that's also, oh, come on, you're not going to make that any larger or a different color or move it somewhere. Oh, and of course, if I zoom in, it does nothing. Well, I'm sorry about that. That's on GeoGebra to make it distinct which one is which. But there's this angle for the first triangle and this angle for the second triangle. And why do they agree? Jillian.
Share like the same like middle angle.
Yes. Exactly. It's a right angle plus this, and this one is a right angle plus that. So the triangles are the same. And lastly, how about the area? Why is the area of ABH 4.93, whereas BKJH has double that area? Leila, please.
But, so the reason it's the same as the small square is because it's compared to like the little rectangle. It doesn't have to do with like the whole square.
Yes, the little rectangle, the BKJH rectangle is what we're going to compare to ABE, whatever that letter is, D, I think. So the reason the square is twice this triangle is because they're between two parallels and they have the same base. So the common base is BE. So both this square, this ADEB square, and this triangle EBC have the same base, BE, and they lie between the same two parallel lines. This line and this line are parallel because they're opposite sides of a square. Well, the base is parallel to the top, and the triangle lies on that top. Alexandra.
Sides, and I partially understand the angle. Like I see where the 90 degrees comes in, but then how do you get to knowing if those angles are equal?
That this angle B and the angle beta are equal. So they share this middle part. And then the way I get to the full angle in the first triangle is I add 90 degrees.
Oh, so they're just the part they share plus 90.
Yes. And on the other side, it's also the part they share plus a 90, a different 90, but all 90 degrees are the same. P4. Okay. This is an instance of where that's needed. So does anyone see why this triangle and this rectangle have this 2-to-1 ratio of areas? Yes, exactly. For the same reason. It's I-41 again, that you have this side is parallel to this line. The rectangle sits here, and the triangle is on that same base and on the same, and its top is on that parallel. Okay, so the argument goes, the square has double the area of the triangle. The two triangles are the same, and the rectangle has double the area of the triangle. Therefore, the rectangle and the square have the same area. Amelia. Yes. Yeah, and then the same argument, Euclid doesn't bother proving it again. He says, that's an argument that applies just as well to the other side as to the first side. There's nothing special about, there is no side, right? I could pull this around and make this over here or something. The argument works just as well. And everything remains the same. Whichever, this square has the same area as this rectangle. Does that make sense? No. Yeah. So Amelia's question was, what about the other side? How do we get that this rectangle, this square has the same area as this now thin rectangle? It used to be the bigger one. And the point is that what we've drawn, what we've proved has nothing to do with what we've drawn. So it's a general theorem. So it applies just as well to the other side. And so this rectangle is the same as this square, and this little sliver is the same as that square, and they add up to make the big square. Okay. Yes. So what I'm saying about parallelograms, let's just isolate that statement. If I have a line and I have a, let's get a point, and let's draw a parallel line from this line to, from this, please. You have to say it very nicely or else it won't do it. Okay, so there's a parallel line. If I draw a parallelogram, how am I going to draw a parallelogram at n. Let me just move n to some random point. I'll take a compass that takes a segment, and then a point. Okay, so now I've moved this distance. This radius is the same as the distance L to M. So if I draw these other lines in, I get a parallelogram. Okay, totally random parallelogram, doesn't have to do with anything else that's going on. There we go. Okay, that's a parallelogram. The area of that parallelogram, so let's make that parallelogram, N, O, M, L, and back to N. The area of that thing, where's my area? Here it is whatever it is. And now I take a top anywhere on this same parallel. Okay, so P is just any point on the parallel line, parallel to the base LM, and I'll draw a triangle from L to M, bless you, to P. Josie, does this make sense? So if I draw a polygon from L to M to P and back to L. So this is the situation of I-41. Let me zoom in on this. Whoops. I don't know what's going on. This is the situation of I-41. You have a parallelogram, any kind of parallelogram whatsoever, and then you have a triangle, any triangle whatsoever that has the same base as the parallelogram, and the top is on the parallel. So if the parallelogram's area is 6.5, what will the triangle's area be? Half of that, 3 1/4. Okay, that's the theorem that we're quoting.
Could we see anywhere and it would be?
Yes, that's the beauty of this theorem. The area does not change.
Is it because it's the same height?
Yes. So if you want to do 1/2 base times height, the base and height are orthogonal, and you're not moving the parallel line. Okay, does that make sense? Okay, Josie. Yes. Yeah, so we're used that theorem twice. The first time is between the parallelogram ABDE, that's this square. There's the base, and then the parallel line, which is just the line straight through DA. And notice that C is on that line. Why is C on that line? Where in the proof have we used the fact that the triangle ABC has a right angle at A? Laurie.
Proposition 546, it says that the one we did before this in the previous lesson that says that if there's a right angle, the other one next to it, straight line is a right angle.
Yes. Yeah, so that's a right angle, which means that's a right angle, which means this thing is a straight line. If I didn't have a right angle at A, then C would not be on the same parallel. If I had a totally random picture, if I take an angle that's not right, let me just draw a non-right angle. Here's C, and here's B, and I'm going to draw a square on here. That's a terrible square, but this is why I do it in GeoGebra. Okay, if I extend this parallel line, there's no reason for C to be on it. And there's no reason for this area to have anything to do, this area, to have anything to do with this area. You see that? It's only because the angle at A is right that moves C up here onto the line. And now they're the situation of I-41 where you have a parallelogram and a triangle on the same base. That's this 2-to-1 ratio. Okay. Let's move on from I-47. Hopefully you haven't, yeah, Alexandra. No, not at all. Yes.
One.
Yes. Yes.
Bigger picture falling out.
Yeah. So you have this triangle A. I mean, you have the square A, capital A. Let's say its area is capital A. Okay. And then this triangle, let's say it has area T for triangle. Okay. And the relationship is that A is 2T. And then I'm going to drop this perpendicular. And that has the same length as that. And this has the same length as this. and this is a right angle, and that's a right angle. So if I draw this triangle, that's the same triangle. Those triangles are congruent, so its area is also T. And now if I drop a parallel line to this line, these two lines are parallel. And I'll put a perpendicular here to finish off the rectangle. So let's call the area here R. Because this triangle lies in the same parallel as this rectangle, we also have that the rectangle has area twice T. Really, there's a T1 and a T2. This is T1, this is T2, but the two triangles are equal. That's the proof.
So the rectangle in relation to the triangle is double.
Yes, just like the square. So these things all together tell us that the area of this square A is the same as the area of the rectangle. Wonderful. Josie?
Like, the triangle doesn't lie, the base, no base of the triangle. Oh, I guess the one thing's on the side.
Yes.
Okay. That was
The- Yes. Yeah, this base is the same as the base of the rectangle, and its top lies on the parallel, which bounds the rectangle from the other side. So there's two different pairs of parallel lines. One is for A and its top, which is over here, and the other one is for R and its top, which is over there. Okay, it takes some thought. So let's move on. But if you want to look over this argument again, it's in your book. You can read it in the original Euclid's Elements. How does Euclid finish the book? Let's just finish off the book. What is I-48? We're finishing off book 1. I-46 is he makes a square. I-47 is he proves the Pythagorean theorem. The second he can make squares. I-48, the converse. The converse. Converse, this is a very simple argument. So if, I'll just write it, if a squared plus b squared is equal to c squared, then the angle at C is a right angle. So let's just draw a little picture. I guess I want C to be the one that has, I'll try to draw it not right. Okay, so that's kind of funny. This is the point C. This is the little segment C. This is the little segment A and little segment B. So this will be the point capital A, that'll be the point capital B. Okay, my claim is that if a squared plus b squared is equal to c squared, then the angle at C has to be right. Okay, let's look at the proof. The first step is drop a perpendicular at C. Make DC perpendicular to BC, and D is some point over here. Then so this is step 1. Why can we drop perpendiculars? We know how to drop perpendiculars. Question? You sure? If you're confused about anything, other people are too. Joseph. I've just drawn it very poorly. I've purposely drawn it poorly, but maybe not poorly enough. Let's make that B and this length is C. How's that? Now it just looks equilateral. This is really bad. But suppose that a squared plus b squared does equal to c squared for some ungodly reason. Okay, and my claim is that angle C is going to end up being a right angle. I've drawn it not right to try to show how, what we're fighting against. Okay, so step 1 is drop a perpendicular to BC. So this is now a right angle. Step 2 is let's mark a point E at the same distance from C as A. Yes, Alexandra. We should. Which one constructs a perpendicular? I'm going to make up a number, 11. I think it's 11. Okay. Yes, please.
No, to drop On the perpendicular, a point which is the same distance as C.
Yes.
A, C,
Yes.
you do that by drawing two circles.
Here you could draw just one. It's
One
an even,
circle, C is separate.
exactly. Yeah, so let's even do that. I wasn't going to specify how you do it. I was going to say what you do, but sure, the way you would do it is to draw the circle with center C and radius CA and let E,
C is also.
exactly. And let E be the points, be the point on DC with EC equal to AC. And AC is what I'm calling little b. So that's why I've marked it this length as little b. Okay. Let me connect BE. Okay, why can you draw circles? Postulate 3, I think, is the one that lets us draw circles. And step 3, let me put it here. Step 3, draw BE. Although you don't really need to draw BE. Why can we draw a line between 2 points?
Two.
1, it's the very first one. 2 is extending a line. If you already have a line segment, you can extend it a little farther. 1 is the first thing you want to do with a straight edge is connect 2 points. Okay, and let's call BE, let's say BE is equal to D. Okay, so this length BE is some unknown length D. What does I-47 tell us? I-47 is about right triangles. BCE is a right triangle. It tells us what about this right triangle? Yes, a squared plus b squared is equal to d squared. We have the Pythagorean theorem. That's what I-47 says. I'll write it in modern notation. Yes, you're absolutely right. The better way to say it is if I were to draw squares on B and A and D, then the squares would add up. But let's just use modern notation. It's a squared plus b squared is equal to d squared. What's our assumption about a squared plus b squared? It's also c squared. A squared plus b squared is also c squared. So c squared equals d squared.
Just like.
This length C, we assumed that we had a triangle, ABC, so that a squared plus b squared was equal to c squared. Now we're trying to prove that the angle at C is a right angle. Okay. So here's, there needs to be a little bit more arguing again than I would say than Euclid concludes, but he says, therefore, C is equal to D. If D squared is equal to C squared, what if the squares are the same? Why are the side lengths the same? There's a little bit of an argument there that one needs to give, but I think I don't have to convince you that that means that the side lengths are the same. Lord. Please.
EC is equal to CA,
EC is equal to AC. Yes.
so that it's not equal to BC.
It's not equal to BC. No.
Yeah.
No. Just a poorly drawn attempt at a random looking triangle. That's why I like GeoGebra. Okay. So what? Well,
Size.
yes, that means by side, the 3 sides are the same. Then these 2 triangles. So by side, whichever one that is, the triangle ABC is actually congruent to triangle A is the same thing as E, and then B and C are the same. And so because the sides are the same, the angles are the same, which implies angles are the same. Angles, correspondingly correspond. Let's say correspond. Alexandra.
Be any of the common notions, or is that not one?
Yes. The fact that a squared plus b squared is equal to d squared and a squared plus b squared is c squared, common notion 1 says things equal to equals are equal to one another. C squared and d squared are both equal to a squared plus b squared. Therefore, c squared is equal to d squared. Absolutely. This is great. Common notion 1. Yeah, if you really want to write down every last detail, you'll get in trouble because Euclid doesn't give you enough to write down every last detail, but it's good. As many details as you can write down.
If you have a problem with this, wouldn't it be kind of obvious that it was already?
Yes.
like- That's just hypothetical.
Would it be obvious that BCE is a right triangle or that ABC is a right triangle? That's what he's trying to prove. No, I don't know. I wouldn't call it obvious. Yeah. But you see, so now we have the angles correspond, and so BCE is equal to BCA. So the angle at BCE is equal to the angle at, that's this way, BCA, and BCE by construction is a right angle. We constructed it to be a right angle. This one is a right angle by construction. And all right angles are equal, yeah. Or things equal to equals are equal, again, common notion 1. So this would be common notion 1, is that therefore the angle at C also must have been a right angle, even though it was not drawn that way immediately, which was what we were trying to prove. Quadrate demonstrate. Okay, the goal was to show that the angle at C is a right angle. Isn't that a bizarre, isn't that a funny proof? You take this random triangle you know nothing about, you construct a right triangle somewhere else, side, using the Pythagorean theorem means that you get the angle. Elitsa? What? Yeah. What's that?
Unless that was the point. Meaning, did we,
Go ahead.
we assumed
We assume nothing about angle C, which is why I drew it in a funny way. If you're confused about the picture, you're right to be confused about the picture. The picture doesn't make any sense.
you have a random triangle.
For which you know that a squared plus b squared equals c squared. It's a little bit less than random.
Okay. And then you have it, that if you have the same thing as a squared plus b squared equals c squared, that's going to be right. Right, that's going to have a right angle, and
Well, this one we constructed to have a right angle. That a squared plus b squared equals d squared follows from the fact that we constructed a right angle at C.
because we dropped a perpendicular.
Yes.
From.
Yes. We constructed a right
They
angle.
have the same sides, then they have the same angles, and where do we get that?
That's side. It's I forget which one it is. 23. I'm just making up the number. Okay. One of the theorems is side. If the three sides of an angle, if the three sides agree, then so do all the angles. Okay. You have congruence from side. And congruence.
We have to say like I 1 and 3. We don't have to.
Yeah, I would. It's better if you know what it says. Side.
And did we just prove side? I don't
No.
know.
No, side was proved. We skipped the proof of side. Yeah. Okay. All right. That's book 1. So the main, I wanted you to see what book 1 was all about, but the main, as always, we want to get the takeaway. Like, let's step back. What's going on? We proved all these amazing things. We developed this axiomatic geometry. And the question that remained, as you saw the structure, for the first, I forget it is 27 or something of these 48 postulates, he does not use the parallel postulate, the 5th postulate. He only uses P1 through P4. Once he starts using it, he uses it at every single turn, gets up to the Pythagorean theorem and its converse, and then he's done with book 1. So people spent the next 2,000 years trying to figure out, shouldn't the 5th postulate, it smells like a theorem, doesn't smell like, right? We talked about this and you saw the video, so you know the answer. But for the next 2,000 years, that's a little too many years, people are debating, arguing, etc., about whether the 5th postulate really belongs Of course, this is not a mathematical, well, it is a mathematical statement. It is a mathematical statement. Whether it belongs as an axiom is kind of an aesthetic statement, belongs as an axiom aesthetically, but there's a mathematical statement here, or mathematically, could it be proved already from the first four? Okay, and there's a beautiful long history to this. So let's just go over a few components of it. This is the kind of thing that there are certain problems throughout the history of mathematics that people just latch onto and they can't give up, and they start worrying about them and working on them, and most of the time it kills people's careers, but sometimes they actually get somewhere. So this became a notorious problem. There's something called Playfair's axiom, and there's 1,000 hundreds of alternative axioms were proposed. Maybe hundreds is a little strong. Let's say dozens. Dozens of alternative axioms were proposed to replace P5. Remember, P5 is really a mouthful. When a transverse line falls on two lines so that the angles on the same side add up to less than two right angles, then when you extend those two lines indefinitely, eventually they'll cross. That's like a really, really big thing. People realize things like there's an equivalent version of the fifth postulate that says, given up a line and a point, there exists a unique parallel through the point. Okay, let me put this here. In other words, if I have a line L and I have a point P, then there's one and only line that's in the same plane as L. I'll call this line M. So given L is a line and P is a point, of course, the point can't be on the line. There exists a unique, this is how mathematicians write unique. There exists, let's do it in words, there exists a unique line M that's parallel to L. Okay, it's in the same plane, and the two never meet no matter how far you extend them. Parallel is parallelism. The property of two lines being parallel is something you can't actually determine if you think about it. What does it mean for two lines to be parallel? Lori.
So if you extend them indefinitely, they will never ever touch, but that's not something you can prove unless there's like a counterexample where they can touch.
Exactly. It's not something that's finitely checkable. This is a very, very subtle thing. Note whether two lines are indeed parallel is not a property that can be checked in finite time. Yes. You're absolutely right. You're absolutely right. So the point I'm trying to make here is you're absolutely right that we have theorems. Actually, yeah, that's a really good point. We do have the definition of parallelism can't be checked. Using the parallel postulate, using some version of the parallel postulate, gives you a mechanism by which you indeed can verify whether the condition of parallelism, drop a perpendicular, for example, or drop any transverse line and check that the opposite angles agree. You drop a transverse line and check if opposite angles agree. The fact, though, that that theorem is correct requires you to, it's a theorem that uses the parallel postulate. Whereas if I just give you two lines and I ask the question, are these two lines parallel? You do not have a way of answering. You start extending them for some distance, and they haven't intersected yet. And will they? I don't know. Maybe this is the wrong way to go. Maybe you should have gone that way. You know, you can extend an inch this way and an inch that way and an inch this way and an inch that way. Then if they do intersect, you'll eventually find that intersection. But like, if they don't intersect, that algorithm doesn't halt, Layla.
Definition where it was like, it's two lines with 180 degrees between them. Could you not just measure for 180 degrees?
Yeah, so that's what this, that's a theorem, and it's a theorem that uses the parallel postulate. We can definitely certify non-parallelism. Well, even that is subtle because, well, if you've extended it and they cross, then you know that they're not parallel, and then you can say, yes, they're not parallel because here's a point that they have in common. But if the sum of the two angles, you see the parallel postulate is, even the statement, even the original statement of P5, Euclid's statement, is very subtle. If extended indefinitely, how far is indefinite? What if the two, remember the two angles need to sum up to less than 180? What if they're 179.99999999999? There's an old Ali about this. You guys don't watch. You don't know who I'm talking about. Never mind. You've never heard of Ali or Borat. You heard of Borat? Ali is the, anyway, same guy. He has a thing where he has a whole lot of nines. He's like, I'm not gonna do an Ali. Okay, so I think I've made the point. This is something subtle, and it's something people really worried about. One alternative is the standard way of saying this. Maybe you've heard of this as the parallel postulate through a line and a point. There's a unique parallel line. An alternate version, and by the way, what do I mean by an alternate version of the statement? What I mean by that is, what does this mean? What does having such an alternate axiom, bless you, alternative axiom mean, or postulate, whatever, postulate's the same thing as axiom. It means that using this axiom, you can prove the other axiom. So using P5, you can prove what we'll call the parallel axiom. And conversely, using the parallel axiom, you can prove the statement in P5, that if the two angles on the same side add up to less than 180 degrees, then you'll extend them and they'll intersect. Okay. Here's another alternative that again will prove all the other ones. The sum of the angles in a triangle is 180. The sum of angles in any triangle is 180. Okay, that's another statement that if you had that statement, you would be able to prove, the parallel postulate and the statement of P5. And that is a theorem from either P5 or from. So these are all alternative axioms that you can add. They all do the same thing. Okay. So what did people start to do, Layla?
Like using P5 with the parallel axiom.
Yes.
As well as using the sum of angles in any triangle to prove that same thing.
Yeah, let's call P5 is the original. Parallel is given a line and a point. There's a unique parallel line. Angles is the sum of the angles in a triangle. In any triangle, it's 180. P5 implies both of these. If you just know P5, you'll prove the statement of the parallel, and you'll prove that the sum of the angles in a triangle is 180. If you know that the sum of the angles in any triangle is 180, you'll prove P5, and you'll prove the parallel postulate, and the parallel postulate proves both the angles and P5. Okay, so they're all completely equivalent to one another. Any one of these is a substitute for the other in your axiomatic system.
So what's creating these if they're all equivalent?
If people were trying to figure out, is there some better way to do geometry? Is Euclid really right in putting this very cumbersome mouthful P5? Some people prefer the parallel postulate. That's probably what you learned in school. How many of you heard P5, the way it's actually phrased? Nobody, right? This is not what's done. But people really latched on, to answer your question, Alexander, people really latched on to this alternative as a possible mechanism by which you can prove the fifth postulate from the others. So if you could assume that there exists some triangle with sum of angles not 180, then you would show, using only P1 through P4, then you would show that P5 is indeed a theorem and not an axiom and not a postulate, right? You see why? Let's say you can prove that if you, let's see, I've said something not quite right. If you could assume that there exists some triangle with a sum of angles not 100 using over and come up with a contradiction and prove a contradiction from there. Contradiction. Then you would show that P5 is a theorem. In other words, how are you going to prove that P5 is a theorem? Well, let's see. By contradiction, assume that there is some triangle whose sum of angles is not 180. Long string of arguments follow. I don't know what they are. And then you arrive at a contradiction. Therefore, for every angle, the sum of the angles in the triangle is 180. Okay? Does that make sense? And so people tried. People tried to make this assumption. So lots of people tried to make the assumption that there exists a single triangle with sum of angles not 180, and see if they could find a contradiction. See if they can follow the logic all the way down to a contradiction. They could follow the logic, writing some kind of strange alternative 100 theorems from those, writing some strange alternative version of the elements until they hopefully arrive at a contradiction. Then they'd be very rich and famous. I don't know about rich, but famous. Okay. So if it's not 180, then it's either more than 180 or it's less than 180. Okay. What if sum of angles is more than 180? By the way, it turns out you only need a single triangle. Let me write this out. Now, turns out that if there exists a single triangle with sum of angles equal to 180, then you can prove the parallel postulate. It's the parallel postulate, or the fact that this alternative statement is that the sum of angles in any triangle is 180. It turns out that if the sum of angles in just a single triangle is 180, you already prove that all other triangles also have to have 180 degrees. There's a slightly based on which postulate? You mean how do you so I don't want to go into the full proof, but if you have a single triangle with sum of angles 180 degrees, then you can construct a unique parallel line to any given line and a point. So let's not go over that. Turns out if there exists a single triangle with sum of angles, then you get the parallel postulate. So if the angle is more than 180, then not just for a single triangle, this would hold for all possible triangles. Okay, so one alternative world is all triangles have angle sum greater than 180. Okay. So Gauss started playing with this. The great Carl Friedrich Gauss. Gauss in the he doesn't really say, I'll explain in a second why he doesn't say, 1810s maybe, starts playing with this with this alternative universe and realizes that there's an extra, if you want lines to be infinitely long, and under the extra assumption that lines are infinitely long, manages to come to a contradiction, manages to arrive at a contradiction. Okay, so if we're assuming that all the angles in a triangle add up to more than 180, and that lines are infinitely long, then Gauss comes up with a contradiction. It doesn't actually tell anybody. I'll come back to that. So what remains is the other alternative world, namely that all triangles have angle sum less than 180. And so this is where we get to a guy named Bolyai. So he starts playing around, okay? He starts playing around. And let me give you a sample theorem. So here's a sample theorem of Bolyai. The theorem says that, so we're in this world. What's the world? Assume that any triangle has angle sum less than 180. In particular, that means any quadrilateral. What's the angle sum in a quadrilateral? If you have any quadrilateral, whatever it is, you can always break it up into a pair of triangles and the angles all add. This implies that angle sum in any quadrilateral is less than 360. So his theorem in this world is angle, angle, angle implies not just similarity, but congruence. This is totally weird. This is not what, like, if the three angles agree, then the three sides also agree. It doesn't work that way in real life, or so we think. And we're trying to rule out this possibility. So let me show you what his proof is. Okay, so we're given three triangles. Let's call them ABC, whatever. And I'll draw DEF, and I'll try to draw DEF to be the same angles, but slightly bigger. Whoops, that's supposed to be an E. Okay, so we're given triangles ABC and DEF with angle A equal to the angle at D, angle B equal to the angle at E, and angle C equal to the angle at F. Okay, this angle matches that angle, this angle matches that angle, and this angle matches that angle. And assume, by contradiction, assume that AB is less than DE. Okay, suppose that AB, the corresponding sides are not equal. They're not equal, one of them smaller. So step one, remember that Euclid's compass is collapsible, but it may as well be fixed. That's I2. By I2, we can draw, let's call this point G, G on DE with AB equal to DG. In other words, if AB is the smaller length, okay, fine, then mark that smaller length on the bigger triangle. Okay. So far, so good. Step two, there's another proposition of Euclid's that says you can move an angle. If you have an angle somewhere, because you can move lengths, you can move angles. I'm going to make up a number, I7, not really, can move angles, So draw an angle at G equal to the angle at B, which is the same as the angle at E. So I'm going to move this angle 2 over to G. These are all things that happen well before Euclid touches a parallel postulate. We're not assuming the parallel postulate to make these moves. Okay? So I have a new point H. Now, A and AB and this angle at B has been moved to D and this length DG and this angle. So by angle, side angle, which again happens before the parallel postulate, triangle ABC is congruent to triangle DGH. Everybody with me so far? So what's the angle at H? It's angle C. It's the angle at C, right? This is 1, 2, 3. And now we have a problem. Let's call this angle, I don't think we need to, I'll let you think about this just in the interest of time. It then follows that the quadrangle GHFE, angle sum in the quad GHFE is 360 degrees. Because this is 180 minus H plus H, and this is also 180. Let me not mark them. This angle is this angle plus that angle makes 180. This angle plus that angle also makes 180. So those 4 angles add up to 360. And that's a contradiction because we said we live in a world where the sum of the angles in a quadrilateral add up to less than right angles. What was wrong is the assumption that AB is less than DE. They can't have different sides. So actually AB and DE are the same, and having the same angles means that the side lengths are congruent. He's like, okay, well, obviously this is nonsense. This doesn't make any sense in terms of geometry, but I can't find the nail in the coffin, the final contradiction. And he proves, 100 theorems of this form. He's writing his own book of elements, and he can't find a contradiction. So Bolyai continues in this way. Failing to find a contradiction, but constructing this crazy new world where the parallel postulate fails. Is false. Sorry.
Clarify, this whole thing is from Bolyai, not from Gauss. At what point did we switch from Gauss to Bolyai?
Yeah, so we're going to get to Gauss and Bolyai right now. I'll explain why I'm giving credit to both of them. So he writes a whole treatise in 1832. I think that's right. I think that's right. 1832, Bolyai publishes a treatise of this crazy new geometry. And his father actually knew Gauss they had worked together a long time ago. So he sends this manuscript to Gauss for comment. Do you guys know what Gauss replies?
Compliment, but it really came across as an insult.
Yes.
Oh, is this the teenager person from the video?
Yes.
The violinist, and he did all these duels and stuff.
That too. Yeah. Yeah. Okay. So you watched the video. Good. And you remember something about it. So right. He was devastated by this experience because Gauss's reply. So you've already heard Gauss's reply. I cannot praise this work, for to praise it would be to praise myself. Ouch. Okay. I cannot praise this work, for to praise it would be to praise myself. worry about the extra credit. Because Gauss himself, as I said, no one knew this. Nobody knew that Gauss was working on this problem and made, we don't know because he didn't release what he had done, but he wrote letters. We know that he wasn't lying. I mean, he's Gauss. He's probably not lying. It would be pretty crappy of him to do that. But in fact, he wrote letters to his friends, confidants, and from the year, I'm going to say 1824, as early as 1824, he has letters that say things like, I'm discovering this crazy world, and he writes why he doesn't release it. And I want to get this verbatim. Doesn't publish. He says to his friend, that he won't ever publish this work, because I fear the howls of my contemporaries. I fear the howls if I speak my mind out loud. This is Gauss. This is 1824. He's already the biggest deal in mathematics at the time. He's working on this stuff, and he doesn't want to be Hippasus. Okay, this is what free speech is about. That you want people to speak their minds even when it goes against everything that's going on. So young people, Bolyai is not established. He wants to make a name for himself. He's willing to put himself out there with this crazy idea that maybe there is this other kind of geometry. And he and Gauss get into this thing where Gauss says, yeah, I thought so too, but I was too scared because I was already so established in my career. I was too scared to say anything. And he writes this in 1824. Not in 1832 when Bolyai comes out with it. He's writing to his friend, I've discovered all these crazy things. I'm not going to say it to anybody. I don't want the ridicule of my esteemed colleagues, even though he's the pinnacle of the profession. He can't say it, Josie. Yeah, so imagine Euclid's elements. You have 48 propositions. Postulates 1 through 4 are the same, and postulate 5 says the sum of the angles in a triangle is less than 180. People go, what are you smoking? Of course it's not. Why are you doing this? This is all wrong. Yes. Yes, it's a total sidestep that's inaccurate until you realize that actually it's not a total sidestep that's inaccurate. There's a whole other geometry that has that. For example, the spheres. But they ruled out the spheres. We'll come back to the ruling out of the spheres in just a second, because in the sphere, the sum of the angles is more than 180. A spherical triangle has more than 180 degrees. They discovered what eventually becomes known as hyperbolic geometry. And it turns out that this world with curvature is exactly the mathematics. They did this mathematics for no reason than to try to understand the parallel postulate. Something really, as a kid, I would think this is the dumbest reason to do math research. Like, just find out the truth. Don't worry about the axioms. Yeah, there's this clunky axiom. Who cares? 100 years later, Einstein comes along. He needs the mathematics of curved spacetime for the general theory of relativity. Mathematicians had already worked it out. But,
Not to go back, but about the thing with the triangle
yes.
and like the sides being the same. I feel like I learned something that was like triangles can have different sides. They just have to have the same ratio. And they will still have the same angles.
Yeah, angle in the real in flat Euclidean space, angle just gives you similarity. You're absolutely right. The true statement in Euclidean geometry is if the three angles are the same, then the ratios of the corresponding sides will all be the same. One is a scaled version of the other. But here in non-Euclidean geometry, it turns out that that's a theorem, a rigorous theorem that we just proved, that if the three angles are the same, actually the triangles are identical triangles. Nargis and Jemima.
Did Bolyai ever do that again?
Yeah, so that's what the story is, that he was so devastated by this reply. He had a 1-2 punch. The first punch was Gauss's reply. The second punch is he eventually went to the library, or someone pointed out to him that in 1829, a Russian, in Russian, of course, Nikolai Lobachevsky had also independently discovered many of the same theorems, discovered and published many of the same theorems. In fact, in Russia, it's called Lobachevsky geometry, what we here call hyperbolic geometry. Okay, so that's the 1-2 punch. Not only does Gauss say, actually, I knew this 20 years before, but I didn't publish anything. I didn't tell anybody except my closest confidants because I was afraid of ridicule. I was afraid of what would happen to my lofty position as a professor at the University of Göttingen. That's on him. That's on him, but of course. Well, that's why, you know,
Top left, the advice from like someone who's like quote unquote wiser, and I have to say like, you shouldn't be speaking.
this is why mathematicians love young people. Young people are too dumb not to do things that we know are impossible. And then they go and do them. Okay, this is why mathematicians care so much about.
Sorry, it's also for mathematics, you have to, or that's part of humanity. Earlier, you have to do your like proper research, which can be really hard if you like try to do something that someone else already did it. Then you don't want to honor for yourself.
Yeah, okay. So if Lobachevsky hadn't published this, then the credit should still go to Bolyai for having published it first. Even though you can't work in it, science does not happen in my drawer. If I prove the Riemann hypothesis and I put it in my drawer, and then 20 years later, someone says, oh, I proved the Riemann hypothesis. I go, actually, I had it 20 years before. Here it is out of my drawer. So yes, that's what Gauss did to Bolyai. It's not okay. The community should give credit to Bolyai because he's the first to publish. That's why there's this standard of you publish, it's not a theorem until everyone knows what you did and can check it. Lobachevsky. You guys don't know this Tom Lehrer song? Nikolai Ivanovich Lobachevsky is his name? Yeah. So it's a joke. It's not, he didn't plagiarize off of anybody. That's just, he liked the name. It fit the rhythm. You guys know this Tom Lehrer song? Oh, I gotta play it. Okay. I'm not gonna play it for you now, but I'll put it in on the page. Elisa.
If you read like their works side by side.
It's different. It's different. But the theorems, the facts, like Lobachevsky has a version of this angle implies congruence. The truths, this is always this question, is mathematics discovered or invented? The truths, which questions human beings decide to ask for whatever reason, it was in the air that this is the question you should ask. And both Lobachevsky and Bolyai decided to ask that question. And then what truths they arrived at from those axioms, that's a discovery. That's a universal fact that we have no control over.
And why so close in time?
This was in the ether. This is not an uncommon thing to happen.
No, because I know we talked about going back, like when we were talking about ancient things that like the what was described about like including zeros.
Yeah.
And that was happening in multiple places where there wasn't communication.
Right.
But was there some like discovery that happened in early 1800s and 1700s that then perpetuated like we should be learning more about?
Not to my knowledge. I think these are completely independent discoveries. There was something about the Renaissance of mathematics. People are revisiting these old ideas and they have, some free time. They have circumstances under which they can think deep thoughts. And both of these young gentlemen decided to take up the challenge. And they both were brave enough to publish their conclusions, despite the ridicule that would surely follow them, which Gauss wasn't brave enough to do. Did I get to you, Jemima? You had your hand up before. Go, please.
So hyperbolic geometry.
Yeah, I haven't gotten to that yet.
Oh, sorry.
Yeah, so this is now called, this geometry is now called hyperbolic geometry.
That's when it's the angles out to less than 180.
Yes,
What's it called when they're more?
spherical geometry. Yeah. Amelia and then Mary. Yeah. I'm going to show you a time. Yeah, I want to actually go into hyperbolic geometry for a minute.
Still afraid that like if they publish something that the majority of people, like the Pythagoreans, how
It's no longer the Galileo thing where the Catholic Church will off you or excommunicate you, but it's still Gauss is worried about the opinion of other mathematicians. Despite being at the pinnacle of his career, he's worried that other people will ridicule him for going down this path that everyone knows is a path to death, mathematical death. Mary.
It's so helpful, that all Greek thinkers are not only children of their time, right?
Yeah.
Actually, they question the status quo. I mean, that always gets you ostracized.
Yeah. Yeah, and Gauss did it himself as a younger kid. He proved all kinds of great things that broke through paradigms that were blocking progress. Yes.
Question whether Einstein would have come up with a theory of relativity if this had not happened.
Exactly right. Maybe he would have had those ideas and then would have taken him 50 years to work out the details. But mathematicians had done those 50 years for no reason. This is what I write in my NSF proposals is let mathematicians do their thing. We don't know how, we don't know when. At some point, we will reap the benefits of questions that mathematicians answer. Okay. Let's talk for a second about what happens at the end. Okay, so Riemann comes back to this question. The great Bernard Riemann. Riemann returns to sum of angles being more than 180 degrees, sum of angles being more than 180 degrees, and realizes that there's nothing in Euclid that says lines have to be infinitely long. Postulate 2 says you can extend a line. So lines just have to be unbounded. Lines merely need to be unbounded, not infinite length. You want to unbounded means you can always extend it in any direction, right? That's what postulate 2. Not infinitely long. So P2 belongs over here, not unbounded. Not infinitely long. So there's nothing wrong. So the way that Gauss initially ruled out this geometry with the some of the angles is more than 180, actually it shouldn't have been ruled out. So should not have been ruled out. And finally, the entire question is put to bed by Riemann is like 1850s. I'll put a random number here, 1855, by Eugenio Beltrami. So Beltrami in 1868 finally puts the issue to bed. Proving that the fifth postulate cannot be proved from the other one, Alexandria. Yeah, so if we look back here, I said Gauss starts playing around with this alternate universe. And the alternative world that he first considers is that some of the angles is more than 180. And he says, well, implicitly, there's this assumption that lines have to be infinitely long, and he arrives at a contradiction if the sum of the angles is more than 180. And Riemann revisits this and says, wait a second, nobody said it has to be infinitely long, it just has to be extendable. But great arcs on the surface of a sphere are extendable. It's just that they're not infinitely long. So there's no contradiction. That's not a real contradiction. Gauss is adding an extra assumption that should not have been added. How? The question is how? How does Beltrami do this? How do you prove that something can't be proved? Just like how do you prove that something can't be constructed? You know, notice this is a crazy time in mathematics. It's the early first half of the 19th century. 2,000-year-old problems are getting settled one after the other. Constructibility issues, trisecting an angle, squaring the circle is going to wait until after Beltrami. How could you possibly prove something like this? What he does, and we're going to have to talk more about this next time, he develops the idea of models for geometry. He goes all the way back. To us, this will make It goes all the way back to undefined terms. Goes all the way back. This is what I mean by the modern version of this is to have undefined terms, to definitions of the plane in which everything takes place, points and lines and circles and so on. What do all those things? What Euclid is doing is synthetic geometry. What do all of the, how do we model? How do we model what's going on in Euclid's or any kind of synthetic geometry? Synthetic geometry. In other words, synthetic geometry is geometry given by axioms of what you're allowed to do. That's what Euclid is trying to do. Euclid gives your axioms for what you're allowed to do. And he should have been agnostic, about a model that realizes those axioms. A model that realizes those axioms. So we're going to have to return to this question. We don't have time today to do it justice, but let me just give you one example. So here's one example. How about actual flat Euclidean space? So what's a model for Euclidean space? How about the Cartesian plane? Rene Descartes, this is from 1630s, whatever, gives us the Cartesian plane. And so by the words, see, really, these words should have scare quotes around them. They're undefined terms. I don't know what a point is. I don't know what a line is. I don't know what a plane is. And gives us the Cartesian plane as a model for Euclidean plane, or the Euclidean plane. So what is a line? So what's the Cartesian plane? It's like, yeah, it's x comma y. It's pair of real numbers, x comma y, right? Descartes says, here's how you should think of a plane. There's an x coordinate and a y coordinate. This is a very novel idea. This is not something that anybody in Euclid's time or for the next 1,000 years understood. X, y for real numbers, x and y. What's a line? It's some equation like ax plus by equals c. What's a point? Well, point refers to a pair of real numbers, x and y, and a circle refers to a circle. Circle is what we think of as a circle. How about in spherical geometry, which we already saw? How about on the sphere? Here's another model. Another model for a plane is surface of the sphere. What is a line in this model? We already discussed. Yeah, a great circle. A great circle. Here's a funny one. We didn't really talk about this, but what is a point? I have to let you go, but let me just make redo. Okay, let's make this point. Here's a sphere. Here's one great circle. Here's another, bless you, great circle. Any two lines should intersect, and at most one point if they intersect. So what must the definition of point be? Yes, two antipodal points on the in the model. A point should mean a pair of antipodal points on the surface of the sphere. So this is actually, this geometry is technically not spherical geometry, but projective geometry. And maybe we'll talk more about that next thing. All right, and then I have to explain to you what that third model is and why you can't, how Beltrami manages to conclude, using the idea of models and having undefined terms, he manages to conclude that you need the parallel postulate in order to do Euclidean geometry. Okay.